Hello, this is Mr. Gilmore with the 2.5 The Part-Whole Theorems lesson. What we're going to see today are we're going to work with some angle relationships and segment relationships. In the future, when we're working with some proofs, we're going to encounter what I like to call tedious work. So what we're going to do to avoid that tedious work is to help set up some theorems now. That way, later down the road, when we encounter some of this work, we can actually jump right over it because we've already proven it with these part-whole theorems. So as we go through these, you're going to notice that each of these part-whole theorems actually have really two parts to them. There's one in which relates segments, and the other part which relates angles. And a lot of the proofs we're going to see today, we're going to do the segment form of. However, the proof of the angle form is going to look just like it. Let's start with the midpoint and the angle bisector theorems. So actually, these can be found on your construction page, which is actually what this Let's Look link takes you to. It takes you over to the construction page for this class. Now, when we look at that construction page, it lets us say, or what we see is we are allowed to construct midpoints on a segment, and we're allowed to construct angle bisectors of an angle. Now, why are we allowed to do that? Well, it's really the immediate consequence of knowing two postulates, the ruler postulate and the protractor postulate. With the ruler postulate, we're allowed to measure and make measure, which means that we know the exact middle of our segment. So if we do that, or if we know that, we can create or construct a midpoint there, thus the midpoint theorem. Every segment has a midpoint, and we're allowed to construct a midpoint on every segment. And the angle bisector theorem says that every angle has an angle bisector. We're allowed to construct that thanks to the ruler postulate and the protractor postulate. There's the halfway theorem. So we may encounter when we have a whole segment being cut in half by a midpoint, we may encounter this, or we may encounter an angle being cut in half by an angle bisector, and we want to say that the whole, or the two halves, are equal to half of the whole, right? The two halves are equal to half the whole. So what we have are the segment version and the angle version, and we'll look at a proof of this as well, okay, in just a second. But the segment version says if C is a midpoint of the segment AB, then the two halves, AC and BC, they're equal, but they're also equal to half of the whole. And again, this is going to help cut some tedious work out in the future. We can apply the exact same story to the angle version. Now, of course, we're going to do this proof working with the segments. However, we could adjust the proof very simply to work with the angle version as well. And we're going to do this column style, which means you're going to have the three columns, the statement, the from, and the by. Let's take a look at the proof. As you can see, it is quite a lot of tedious work, and you'll notice that a lot of our reasonings boil down to some sort of algebraic reasoning. And so to avoid most of that in the future, that's why we're proving this halfway theorem now. So if we do encounter a segment or an angle being bisected, then we can call the halves equal, and we can call them equal to half of the whole. So let's take a look at what this proof breaks down into. So we're given that C is the midpoint of segment AB, which means immediately in statement 2, I can call the two halves equal to each other. AC is equal to BC by the definition of midpoint. But midpoint says something else about the segment. It says that the point C is on the segment. So I mentioned that in point 3. C lies on the segment AB, again by the definition of midpoint. What does that follow then? If I know that C is on the segment, it follows right into the segment addition postulate that says that the sum of the two subsegments is equal to the whole segment. So AC plus BC is equal to the whole segment AB. What am I going to do with that? Well, I already know that the two halves are equal to each other, which means I can take BC out of that equation and replace it with AC. So look at step 5. I've replaced BC with AC, and that's just substitution property. Using substitution property again, I can simplify that to 2 times AC equals AB. Then, dividing both sides by 2 using the division property, I will then arrive to the conclusion that AC, which is one of the halves, is equal to half of the whole, right? Half of AB. That's substitution. Our very last statement says, well, what about the other half? Well, sure enough, I can replace AC with BC, and again, I find that the half is equal to half of the whole. That's going to come in handy. Again, it's going to remove a lot of the tedious work that we find inside of a proof. So consider in the future, if you ever see the need, you can consider, hey, I can justify this with the halfway theorem. Let's take a look at this one. I like this one. This was a really handy theorem, especially for some tedious work in the future. It's called equal wholes equal halves. So imagine with me, I draw two segments of equal length. Okay, so picture that, two segments of equal length. Now I cut each of those segments in half. What can I say about the halves? Well, if the whole segments were equal and I cut each of the wholes in half, that means the halves are equal. And we're going to prove that with the equal wholes equal halves theorem. So this can be applied to segments and to angles. So if we read when we read the conditional, you'll read it and you see that I'm mentioning both segments and angles. So it says if two segments or two angles are equal and each is divided in half, then the halves created are equal. Or really, if we want to shorten that conditional, we could say halves of equals are themselves equal. So halves of equals are equal, right? So you're going to do this one yourself on the problem set, but I would like to show you what the diagram that you should be using to tackle this equal wholes equal halves. So here's our diagram. We're given two segments, AB and DE. Now, C is the midpoint of the first segment, and F is the midpoint of the second segment. But notice that what we're given that the wholes are equal, so equal wholes. So AB is equal to DE. With C being the midpoint and F being the midpoint, we have information about what we know about these equal wholes, right? And with the midpoint, that's halfway, isn't it? I wonder if you could do the halfway theorem to help you prove this one, right? To show that the halves are equal. Now, all you're showing in this case is that AC is equal to DF. Okay, you're showing only AC is equal to DF. However, what would immediately follow is we would know by substitution and transitivity that all the other halves are equal to those two halves there. So equal wholes, cut them in half, we're going to have all equal halves there. The good old MPT, the many parts theorem. Now, we have seen segments and angles already being divided up into sub-angles and sub-segments. For example, if we were working with or working with a segment with a point on the interior, then we know it's divided up into two segments. Now, we can apply the segment addition postulate. Same thing goes for the angle addition postulate. If I know if I have an angle and I've got a point on the interior, then the ray that from the vertex through that point, it divides my angle into two subangles. Now, the sum of those two subangles equals the whole. That works great when you only have two parts. But what the many parts theorem covers is if you have two or more. So naturally, if you encounter just two parts, just throw segment addition postulate or angle addition postulate at it. But what if you have three parts? What if you have 10 parts? That's where the many parts theorem comes in play. Let's take a look at a diagram with the many parts theorem. I've also got the proof here for us. So here is a diagram of a segment. Now, of course, this is the segment version. To prove the angle version, it would look very similar and the flow would be the same. So I have this segment AB with 2 points on the interior, C and D, which means I have 3 subsegments. What we're going to prove then is that the sum of those 3 subsegments equals the whole segment. And it's very simple. You'll see down in the red text, this is the proof, and I did paragraph form on this one. So we are given segment AB with points C and D in its interior. Well, by the segment addition postulate, now remember, the segment addition postulate only works with 2 segments at a time. So notice that I'm going to work with only 2 segments at a time, or 2 parts at a time. So the segment addition postulate says that if I took AC plus CB, it equals the whole segment AB. But notice what I'm going to do with that segment CB. In the next statement, again using the segment addition postulate, I say that CD plus DB equals CB. So those 2 parts CD and DB equal that whole segment CB. But with replacement, with substitution, I can take CB out of my first equation and replace it with its 2 equal the sum of the equal subsegments CD plus DB, which then means I end up with AC plus CD plus DB equals AB. And if I show this with 3 parts, then it'd be very easily to reproduce with 4 parts or 5 parts and so on and so on. So with this proof, It's enough then to capture the many parts theorem. And of course, this applies with angles as well. Equal parts equal wholes. Let's say we have, again, this applies to segments or to angles. Let's say we have two segments in which we know the parts of those two segments are equal. So I could then say, if I know that the parts of the two segments are equal, I could then justify by saying that the whole segments are equal. All right. So if we can pair off parts of two wholes so that the paired parts are equal, then the wholes are equal too. Now you're going to give the proof of this one on the problem set. Okay. Of course, you're going to do segments, but the proof using angles is very, very similar. You're just using different, different reasonings. Instead of segment addition postulate, you'd be using angle addition postulate. But with that very minor detail change, you still capture the whole this with the proof using the segments. Here is the setup of this proof. Now, of course, you're still going to do this one on your own. Um, I would recommend doing it paragraph. You can do it column wise if you want to, but honestly, doing this one paragraph, it would make it a lot easier. So take a look what we're having here, right? We have two segments, A, B, C, D. Now, I didn't give the whole given. Okay, technically in the given, I would also say that point E is on the interior of segment AB, and point F is on the interior of segment CD. But what I've given you also, which is the important part, which is that AE and CF are equal in length, and EB and FD are equal in length. So prove then that the wholes are equal. The whole segment AB and the whole segment CD are equal. Segment addition postulate is going to come in handy on this one. All right, so make sure you use that one wisely in approach to the equal parts, equal wholes. The whole minus part. Okay, the whole minus part. This one it reads a bit different, but what you're going to find when we see a diagram of this, that it will make sense once you kind of unravel what the statement's saying. So let's say you have two wholes, and again, this could either be segments or angles, and we know that those two wholes are equal. Well, let's say that there are a set of parts that make up the wholes, and we know that those parts are equal. If I were to subtract those parts off of the whole, what could I say about the remaining parts? Well, I'm taking equals from equals, which means I would know that the remaining parts would be equal. So let's prove that. So if I have, again, two wholes, either segments or angles, and we can pair off the parts of the two wholes in such a way that all pairs except for one are equal, then that final pair has to be equal too. And this will make more sense when you see the diagram. So you're going to prove the segment version on the problem set, but let's take a look at the diagram of what you're going to use to help you prove this. So we're going to use these two segments again here, A, B, and C, D. Again, I didn't mention the whole given. I would say the whole given would be segments AB with point E on the interior and segment CD with point F on the interior. Okay. But here's what you're going to prove, that if we know the wholes are equal, so again, AB and AB equals CD, and we have a pair of parts that are equal. So if I say that AE and CF are equal, prove to me that the remaining pair of parts, right, we've paired off the parts, and there's one final pair. If we pair those together, you're going to prove that they're equal in measure as well. So prove that BE and DF are equal in measure. All right. This is going to make good use of the subtraction property, okay? Because you're going to see some equals taken away from equals. It's a very simple proof, okay? Very simple proof. All right, this last proof we're going to prove together, okay? You'll see the proof on the last slide. This is called the whole greater than the part, all right? Or W greater than P. We've seen already that if we have the sum of two parts equals a whole, I can declare the whole greater than a part by the definition greater than. But what this whole greater than part says, it's actually a bit broader than the definition of greater than. This one says that if a segment, or again an angle, you'll do the segment version, or I'll do the segment version with you in a second. But if a segment or an angle, right, is divided into parts, then the whole is greater than any of those parts that make up the whole, right? So I can take it a step further by saying that the whole is greater than any of the subparts. And the whole greater than the part is going to help us, again, cut out some tedious work in the future. I'm going to do this one paragraph style. So on the next slide, I have a simple diagram. I have our given and proof statement already laid out, and then in the red text, I have the proof in paragraph form. So the diagram is very simple. I give you a segment with point C on its interior, and it means I've divided that segment into two subsegments. Let's prove that the whole is greater than both parts. And it really is very simple because what I'm doing is applying the definition greater than twice. Okay, I'm applying it twice, taking the whole and showing it's greater than one part, and then taking the whole and showing it's greater than the other part. And remember, when we're working with segments and angles, all of these have positive measure, which allows us to apply the definition of greater than. So we are given segment AB with C on its interior, but so then by the segment addition postulate, AC plus BC equals the whole segment AB. Well, then by the definition of greater than, I can declare two things. AB is greater than AC and AB is greater than BC, right? So the whole will always be greater than the part. I can cut the segment into more subsegments, and however many subsegments there are, the whole will always be greater than any of those subsegments that we find. With that, that concludes our 2.5 lesson on the part-whole theorems. Be sure to be working on the 2.5 worksheet. If you have any questions, email me about that. Be good and do good.